May-June 2022, Paper 4, Variant 2. Question 1a. So this question is a solubility of group 2 hydroxide, and it's already give a statement that this group 2 hydroxide, the solubility increases down the group. Before you answer this question, you must know the relations between the solubility and these solutions enthalpy. So when the solution's enthalpy or enthalpy change of solution is more XO, so the solubility will increase, means it will dissolve more. This is a relation. And in this question, since already give you this statement, so you need to explain why it become more XO down the group, because more XO, more soluble. So therefore, you need to use two enthalpies to relate to this enthalpy change of solution, which is the hydration enthalpy and the lattice energy, these two. And you need to mention the difference between them. Okay, I will try to use two example or two enthalpy change of solution to let you more understand on the statement. This is the answers for mark scheme. So why they give this answer and how you can explain it well later. So first you must understand what is a comparison. So down the group, the hydration enthalpy and lattice energy both become less XO, or we say that both decreases. So why? It's because the cation size, when down the group, the cation size become larger, so the attractions between the species is become weaker, release less energy. So therefore, the first point that you need to mention is both hydration and lattice energy become less XO. Okay, again, hydration enthalpy is the energy release when gaseous ions is dissolved in water, a large amount of water. The lattice energy is the energy release when the gaseous ions combine and form the compounds. So this is the both exothermic terms. So for this example, magnesium hydroxide and calcium hydroxide, as you can see, both hydration enthalpy and the lattice energy, they are exothermic. When down the group, as you can see, the hydration enthalpy decreases by this amount, 329, and is become negative 2482. For this lattice energy, as you can see, is decreased more than the hydration enthalpy, which is 459. So it's from negative 3087 to negative 2628 kilojoule per mole. So why this one decrease more? It's because the lattice energy now is the dominant factor, or we say that main contributor. Why? Because the size of hydroxide is relatively smaller than sulfate now, because there is a solubility of sulfate and solubility of hydroxide. So because hydroxide, the size is small, and the lattice energy now is affected by the cations and the hydroxide both. And of course, the cation's contribution now is more, is dominance. This is the reason why when the size of the cation increases, so the values of this lattice energy decreases, because now the size of cation is the dominant factors for this lattice energy. Okay, I hope you understand what I say. If you don't understand, so please now refer to the values as you can see. Because the lattice energy now decrease more, the lattice energy for this calcium hydroxide now is smaller. And these negative values, the hydration enthalpy, now plus a smaller values. So eventually, it will give more exothermic values compared to the magnesium hydroxide. Magnesium hydroxide is 276 and the calcium hydroxide is 146. So it just because, as you can see, it just because of the lattice energy decrease more. So eventually now the solution's enthalpy become more exo. That's why second point you must mention, decrease, which one decrease more? Lattice energy decrease more than the hydration enthalpy, and therefore the delta H solutions now become more exothermic. Part B. The solubility of beryllium hydroxide in water is given 2.4 times 10 power negative 6 gram per dm cube. So later we need to convert to mole per dm cube. And part 1. Write an expression for the solubility products, the KSP, for this barium hydroxide and give its unit. Before you give the KSP, it's actually better for you to give this equilibrium so you can make sure the expression is correct. Barium hydroxide will form the barium 2 ions and 2 hydroxide. So it's 1 to 2 mole, which means when X mole of barium hydroxide is dissolved, so it will form X mole of beryllium 2 ion and 2X mole of hydroxide. The KSP therefore is quite easy now. It's a concentration of the Be2 times the concentration of hydroxide square. So the unit is very easy. So it's mole per dm cube times mole per dm cube square. So eventually you get mole cube dm negative 9. After that, you need to calculate the KSP for the barium hydroxide. As I told you just now, the gram per dm cube you need to convert to mole per dm cube. So 2.4 times 10 power negative 6 over the molar mass. Because gram over molar mass you get mole. So you get 5.58 times 10 power negative 8 mole per dm cube. Okay, so this one is a solubility of the beryllium hydroxide, which is the X here. So you need to substitute this X value into KSP, then you can get the KSP values. So from here, as you can see here, if we try to use X, means X moles of the salt dissolved, so it will form X mole of Be2 ions and 2X mole of hydroxide. So therefore, you need to substitute X and 2X here. Eventually, the KSP is 4X cubed. So again, the X now is a solubility of the salt in mole per dm cube. So you need to substitute this value into this expression. So 4 times this value, this solubility. So eventually you get 6.95 times 10 power negative 22. Part C. Beryllium hydroxide is soluble in aqueous solution containing excess hydroxide ions. From this complex, the beryllium with 4 hydroxide. And this complex is similar to this tetrachloro copper. So this one, no choice. You must remember and you must know what is the geometry from the copper complex ion, right? So the cobalt and the copper with 4 chlorides, okay, means if let's say this is cobalt with 4 chloride and now copper with 4 chloride, both they are tetrahedral. So you need to remember this. So this one is tetrahedral, means it's something look like this. So 4 dative bonds with the chloride, and means the beryllium hydroxide will look similar. So now part 1. Define the terms complex ion. So an ion formed by central metal ion, in this case is beryllium or the copper, which datively bond to one or more ligand. So all this bonding, as you can see, copper with chloride here, they are dative bonds. So these ligands will donate lone pair to this metal ion, so it forms these dative bonds, right? Part 2. Draw a 3D diagram to show the structure of a complex ion. Beryllium hydroxide means 4 hydroxide. Yeah. So you just try to draw similar to these tetrachloro copper ions. So make sure it's 2 normal line. One wedge line shows that is point to front. One dash or dotted line point to the back. So put all 4 hydroxide there, right? So square bracket and 2 negative. So the shape is tetrahedral. Part D1. Explain why transition elements can form complex ion. So why the transition elements always can form octahedral, tetrahedral, square planar, or this complex ion? Okay, it's very easy. First, we must make sure the transition elements, they must have empty orbitals, especially d orbitals. Why? I try to give you one example, like the Fe2. Fe2, as you can see, is argent. These 3d6. So this is 1, 2, 3, 4, 5, 6. So as you can see, this for example, this iron 2, these d orbitals is not fully filled, so it still can gain the electron. Right. So that's why first things we need to make sure is they have the d orbitals that are energetically accessible. Energetically accessible is actually kind of like the d orbitals is highest energy level, so is more accessible, means when the ligands approach, so the ligand can easily form the bonds with these 3d orbitals. That's the meaning. Okay, or they have the empty d orbitals to accept the lone pair from the ligand. So they must have the, let's say, it means they must not be fully filled, or else it cannot accommodate the lone pair from the ligand. That's the main concept. Why they can form complex ion, or why they can form the dative bonds with the ligand in order to form this complex ion. They must have the d orbitals, which they are easily or energetically accessible. That's the meaning. Yeah. Part 2. Complete table 1.1 to show the coordination number of each ion and shapes and the overall polarities. So we have 3 complex ion here. So the first complex ion is something look like this, the cis isomer. Okay, because it's mentioned cis, so we is something like this. And the second complex ion is this, silver with 2 ammonia. And the last complex ion is this one. Of course, you no need to draw like what I did. I just try to show you how it looks like, so it's easy for explanation. Now for this, the shape for the complex ion, the first one already given is square planar, so it must look like this. So it's cis, right? And coordination number is 4 because 4 dative bond here, 1, 2, 3, 4. And of course, this is a polar. When we want to identify polar or non-polar, we need to make sure the dipoles cancel or not. Because let's say, for example, chloride is here. It's because it's square planar. the one that opposite means this one is not the same ligand. So the dipoles cannot cancel. That's why it's polar. If let's say now it's a trans isomer, of course this one cannot really form trans. If let's say it's a trans, it might be a non-polar. But for this complex ion, it's confirmed to be polar because the dipoles cannot cancel. For this second complex ion, this one, yes, because it just this silver is have the two same ligand, the ammonia. So and this one is opposite, means the dipoles can cancel and they are the same ligand, so same dipoles and they can cancel out, so therefore it's non-polar. So the geometry is linear because it's 180 the bond angle, and coordination number is 2 because 2 dative bond, and it's non-polar because dipoles cancel, same ligands, opposite direction. So for this last complex ion, the ion with this oxalate, 3 oxalates, this is a bidentate ligand, and it's 3 bidentate ligand which look like this, is octahedral complex. So the shape is octahedral. Coordination number is 6 dative bond, 1 2 3 4 5 6, and of course this one, they are all the same ligand. Therefore, the dipole can cancel because they're going to pull to different direction and it's the same ligand. So the dipoles can cancel. So it's a non-polar complex ion. Part E. Define stability constant. This one, no shortcut. You just try to remember. The equilibrium constant for the formation of the complex. Okay, I try to use the equilibrium one. Let's say now we want to form the nickel with 3En, this complex ion. This is the new complex form. From where? From its constituents ion. So the complex ion in a solvent normally is water, from its constituents ion. So this is the definition of K step. So it's always from the hexa-aqua complex ion, right? Now, so we have for this part 2, we have 2 equilibrium. The hexa-aqua nickel 2, okay, the first equilibrium is with 3En. So it's from this complex ion, and the K step is this. And equilibrium 2, same complex ion, hexa-aqua nickel 2 with 3Tn from this complex ion, and the K step given. So we know that this is larger than this. Okay, so before that, construct an equation or expression for the stability constant for equilibrium 1, expression for the K step for this equilibrium 1. So first you must know it's about concentration. It's the concentration of the new complex, means the products, over the concentration of the reactant, means the constituents ion, the hexa-aqua nickel 2 and these ligands. One very important things that you must know, we normally don't include the water because water is a constant. It's a constant. So we not really include this H2O in the K step. So we just include the 3 species. And another things that you need to make sure is you need to make sure it's a concentration. You must put a square bracket outside there. Means you try to give the, let's say, nickel with 3En, okay, 2 positive, and after that you need to put a square bracket outside to show that it's a concentration of these ions. So do the same thing for this hexa-aqua nickel 2 and the En. So En here need to be power 3 because the coefficient is 3, right? So you want to get the units is very easy because the concentration is always mole per dm cube, and this concentration also mole per dm cube. This one is mole per dm cube bracket cube. So therefore eventually you get this, right? So you just cancel out. Okay, so you get mole negative 3 dm 9. Part 3, the last one. Describe what the case step values indicates about the position of equilibrium for 1 and 2. You must discuss these two together. Means from these two value, what you know about the equilibrium. So it's more towards left or right. That's the meaning. So from this value, we know that it's very large. Means the concentration of this product is much more larger than these reactants. So therefore, we know that equilibrium will lie to the right or the product side. And second question is, use the case step value to deduce which complex is more stable. From here, we know that the first case step is much larger than the second case step. So we know that the concentration of this nickel with 3En is more, so it's more stable, because more stable is 4 mole, right? So therefore we know that from this the case step value, the nickel with 3En is more stable, right? Because the case step is larger. Okay, that's all. Thank you.